Whenever you start a new maths problem, what's the first thing that you do? Do you pick out key information, formulas that you might need, highlight important data? Whatever it is, I guarantee you your first thought is not, how do I make this problem harder for myself? At least, I hope it's not. But for the problem we discussed today, that is exactly what you should do. Buffon's needle problem is a problem first posed in the 18th century by Georges-Louis Leclerc, Comte de Buffon. Excuse my accent, please. And it comes with a rather ingenious solution. Imagine you have a wooden floorboard with parallel grooves distanced 2D apart. Throw a needle with a length d onto these floorboards. What is the probability that the needle crosses one of the grooves? We can generalize this as a singular line of length d thrown onto a plane covered in parallel lines 2D apart. We should start off by rewriting this probability as an expected value, the average outcome over a large number of repeats. This will be 1 times the probability of the needle crossing one line plus 2 times the probability of the needle crossing 2 lines plus 3 times 3 lines, and so on. However, this is very simple in this scenario, as the needle will only ever cross one line. So the expected value will be a number between 0 and 1. We will call this expected value p. Here's where it gets interesting. Let's double the length of the needle. Now it is 2d in length. How many lines do we expect it to cross in terms of p? Well, simply split it back up into its 2 original needles, and we can see this expected value will be the sum of the expected values of the 2 needles, which is p. So the total expected value will be 2p. Going a step further, visualize a needle bent into an equilateral triangle with each side d in length. What is the number of lines we expect this to cross? Again, split it back into the 3 original needles, and we can see that this expected value will be 3p. Same can be done with this hexagon, this octagon, this icosagon. But what about this circle with a radius of 1 needle? Well, its perimeter will be the equivalent of 2 pi needles, so we expect it to cross 2 pi p times, right? Yes, this is in fact the case. But look closer. Throw this circular needle onto the plane. It crosses 2 times. Throw it again. It crosses twice again. Well, weird. It crosses twice a 3rd time. In fact, if you haven't spotted it already, this circle will always cross 2 times. Therefore, we know that the expected value is 2. But we also said it was 2 pi p. 2 pi p must be equal to 2. We can now rearrange and calculate p as 1 over pi, which is also the probability that the needle of length d crosses a line at all. It's roughly 32%. It can be scaled up and down in relation to the ratio between the length, L, of the needle and the distance between the parallel lines, t. To get the formula, P equals L over pi t. Note, however, this only applies when L is smaller than t, as if it were larger, there is a possibility of more than one crossing. The calculations become more complex, but if you are interested, watch until the end. Approaching this problem from the beginning, you might have been surprised to see pi materialize seemingly from nowhere, but by complicating the problem so beautifully, you feel it could only ever have been this way. Interestingly, this calculation does have a practical use in estimating pi. Toss a needle onto a floor with gaps between the floorboards double the needle's length. Tally the total number of times that a needle crosses a line. Obtain a proportion of successful throws to the total number of throws. The reciprocal of this value will be approximately pi. Now for the harder stuff. While the elegant method discussed before requires no calculus, it becomes necessary for needles longer than the gap between the floorboards. The needle can fall in different distances and angles relative to the floorboard grooves, and we need to consider all of these distances and angles. From this, we could calculate the probability of an intersection. We first define the length of half a needle as d, and the horizontal distance from the center of the needle to the nearest vertical parallel line as x. We then define angle theta, which is the acute angle between the needle and the vertical line that goes through the needle's center. It will be between 0 and pi over 2 in radians. For any value of x, we need to know when the needle will and won't intersect a line. For this, we can use trigonometry. This length here, the horizontal length, is equal to d sine theta. It is clear then that there will only be an intersection when d sine theta is greater than x, or x is less than d sine theta. You can plot these values on a graph which would look something like this. The area under the line that we plot on the graph will represent the positions of the needle where there is an intersect, and the area of a graph as a whole represents all of the positions that the needle can fall. The probability of an intersection will be the area under the line divided by the area of the graph. We know that this this rectangular area of the graph will always be x pi over 2, and we can obtain the area under the line by integration. Let's check this method with our values from earlier. We draw a graph of x is smaller than 1/2 sine theta. The integral of this will be negative cos theta over 2 in the range 0 to pi over 2. This gets us 1/2. Divide it by pi over 2 and we get 1 over pi, just as before. And there you have it. Making things harder just to make it easier, and then making things harder again just for the sake of it. Buffon's needle problem. Au revoir.